All right, guys, for the final lesson of the chapter here, we're looking at part 2 of 10.4. We're going to focus on z-scores and normal distribution. So a z-score will tell you how many standard deviations away from the mean a certain point is. Right? So as we've talked before about normal distribution, and you guys saw within that bell curve, so here's our bell curve. All right, so remember we always had the mean in the middle. And then from there, we were branching out by standard deviations. So if we were to move one standard deviation to the right, whatever this value is would have a z-score of 1, because that's how many standard deviations it is away from the mean. If you were to go one standard deviation to the left, this guy would have a z-score of -1. So again, z is just a measure of how many standard deviations you are away from the mean. The book deals much more heavy with z-scores than is probably necessary, because I'm going to show you guys how we can do a lot of this on technology without the use of z-scores, but we still want to keep this idea involved of z-scores because you do need to understand what they are, and there is a use for them, just not quite as big of a use right now as some of the other areas that you might deal with in statistics. So a quick reminder on one of the things that we talked about with our normal distribution curves. When we did this in our previous lesson, we did not need calculators for this because we were working with values that were in exact standard deviations from the mean. And so there's certain percentages that always work when you're dealing with certain standard deviations. And so quick reminder. So remember, the mean always goes in the middle. So in this case, they were saying the mean is 69.2. So that's what would go into the middle. And then from there, we are moving by 2.8 increments. So if I were to go 2.8 units to the right, that would be one standard deviation to the right. So if I added 2.8 onto this, it would be 72. Right, and so I could keep going by standard deviations left and right, but what I wanted you to see on this is notice that this one talks about the percent or the area under the curve between 65 and 70. Well, 70 is not one of the numbers within our graph, right? And so when we were doing things like this before, they were giving us specific values that were whole number standard deviations from the mean. Right, so like this, we knew this represented 34% of the graph. And so that's great if they want to know what's the probability of getting between 69.2 and 72. But if we want other numbers, then we need a different way of doing this. Okay, and so this is where z-scores come in. So I want to show you how it works with the z-score, but I also want to show you a quicker way of doing it. Okay, and so looking at this example, here's kind of the process that they're going to introduce to us. So here's that same information. Trying to get a little closer for you. Again, you can see we put 69.2 in the middle. We have one standard deviation, or sorry, 72 was one standard deviation to the right. So this would have been our 72 right there. But you'll notice the numbers they're using are not landing on standard deviations. They're in between the numbers. And so here's what they did to apply the z-score formula for this. They said, okay, well, how far below the mean is 65 and how far above the mean is 70? So if we use our z-score formula, so there's our data value, that's the mean, that's the standard deviation. So by using that formula, we can see that 65 is 1.5 units, or I should say 1.5 standard deviations below the mean. And if you use the same z-score formula for 70, we find out that 70 is 0.29 standard deviations above the mean. So that then represents this light gray area that you see under the curve. And so they're saying, okay, so what we're trying to find is the probability of anything that is 1.5 units below the mean to 0.29 units above the mean. Right? That's the area or the probability that we're trying to come up with. Right? And so you could use a calculator for this. So let me just show you within the graphing calculator. I'm going to go back into my distribution function, and we're going to go to normal cumulative distribution function. Looks like normal CDF. So we're going to do that. It's cumulative because we're not looking at a specific point. We're looking at the entire area under the curve, right? It's a whole range of answers. It's a cumulative area. So as far as the lower boundary goes, the lower boundary is the negative 1.5. The upper boundary is the 0.29. The mean they gave us. So here's where it gets a little weird. If we're using z-scores, we always assume that the mean is 0 and the standard deviation is 1. So under these conditions, that's when we're going to be working with a z-score like this. So now if I just hit enter, that's where they're getting their percent from. Okay, and so again, what's weird about this is what you call a standard normal curve. In the standard normal curve, the mean is 0 and the standard deviation is 1. But we only use the standard normal curve when you're working with z-scores. Okay, so if I'm working with z-scores and I want to put in these values as my lower bound and my upper bound, well, then I want the standard normal numbers, which is 0 for the mean, 1 for the standard deviation. So that's all well and good, but there really is a simpler way of doing this in a calculator like this, and I can show you on Desmos too. The simpler way is if I go back under distribution, normal CDF, let's put in the real numbers, right? My lower bound was 65. My upper bound was 70. My mean was 69.2. And my standard deviation was 2.8. So I can just put in those numbers directly. And I still get the same answer, right? So in fact, this is actually even more accurate because when this was calculated, it was using a rounded number, not an exact number, right? So now by putting in the exact values that were on the curve, we actually get a more accurate response out of that. So you see what they got as their z-score for the upper bound was a rounded number, right? It wasn't exact, and therefore that's why their response is actually a little bit inaccurate, right? This would be a more accurate value here. So again, I do want you to understand the z-score formula. There will be a need and a purpose for that. The one biggie that you really have to separate then is when I use z-scores as my lower bound and my upper bound, I got to keep in mind that I'm then using what they call the standard normal curve, which is the mean of 0, standard deviation of 1. You would only put in the real standard deviation and the real mean if you're using the actual numbers on the graph. Let me do another one with you. So what have we said? Over 6 feet tall, right? Over 6 feet tall. So obviously let's convert that to inches here. So 6 times 12, 72. So over 72. Well, if you look at this one is actually a value on our curve, right? We learned already that if everything to the right of the center is 50% and this much is 34%, we know this area must be 16%. However, that's still an estimate, right? The percentages that we were given in the previous lesson were approximations, right? This area is not exactly 34%, and this is not exactly 16%. Those are rounded numbers. So if we really want to get accuracy on this, we need to use some form of technology to do this. So let me show you this one on our calculator as well. So if you were going to use z-scores, keep in mind they're saying greater than 72. Okay, so here's what that would look like. Using the z-score formula, they're coming out with 1, and that makes sense because 72 is exactly 1 standard deviation above the mean. So that's why the z-score is 1. Okay, and so that's all totally fine. So I could go from 1 to infinity as my boundaries, right? And so we could use our distribution function that way. So my lower bound is 1. My upper bound would just be basically infinity. So as long as you just put in a supergiant number right now, it's going to work just fine. There's actually a way of putting in infinity. It looks like this. But if I'm going to use a z-score, then my mean is 0, my standard deviation is 1, and there's my percent. So you can see it's about 16%. It's not exact, but it's close. This is obviously more accurate than what numbers we've used in the past when we just said it was 16%. So that's the way we're using z-scores and the standard normal curve. If you wanted to sort of skip the z-score step and just go to distribution and this guy, so now if we wanted to use the actual numbers on the graph, right, if we wanted to say it's everything greater than 72, then 72 becomes my lower bound. Infinity is my upper bound, because I'm going from 72 to the right. Let's put in the real mean, which was 69.2, and the actual standard deviation, which was 2.8. And there we go. So exact same answer, and in this case that made sense because the z-score that was used here was not rounded. It was exactly 1, right? And so that gave us as accurate of an answer as we could get because we didn't use any rounded numbers here. So anyway, we can do it with z-scores. We can do it with the actual numbers on the curve. We could do it either way. Well, let me show you how some of this can get worked out in Desmos. All right, so let's switch over to Desmos for a minute. So within this guy here, if you bring up your calculator, choose functions, go to distribution. Right here you have the option for normal distribution. And so this tells you right here the two things that you're going to be putting in. So they want you to put in the mean, and then a comma, and then the standard deviation. If you leave it as it is right now, if you kept 0 and 1, then you're using the standard normal curve, and you're dealing with z-scores. But typically it's easier just to deal with the actual numbers on the graph. So I'm going to go back to the very first one that talked about the percent or the probability between 65 and 70. So first things first, let's put in the mean, 69.2, comma. Standard deviation was 2.8. And so for these guys, before I even actually choose specific values, if I wanted to actually see the graph, just click this guy right here, and there's your bell curve. All right, so super cool. So now if you want to start working with some real numbers, just click on this guy that says find the cumulative probability, cumulative distribution function, and this is where you put in the boundaries. So when they said between 65 and 70, that just means your minimum is 65, your upper is 70, and there you go. So it not only, let me get rid of this, it not only shows you that on the graph, that shaded area, but it also gives you the percent right there. So super easy. What if we wanted to do the second one that said over 6 feet tall? Okay, so one of the nice things about this is you just keep this as it is. That doesn't change. But if we wanted to say everything greater than 72, that makes 72 my lower bound. And our max is going to be infinity. I want you to notice something. Infinity is the default. So I don't actually have to type in infinity. Okay, that's automatically there. So if I put nothing there, the default is infinity. The default for this guy is negative infinity. So you never actually have to put those in, right? But you can see, right, this represents everything from 72 to the right, so greater than 72 inches. Gives me the probability, gives me the graph. Nice and easy. All right, so one last one on here. So again, shorter than 5'6". So first of all, you got to convert to inches, right? So we did 5 times 12 is 60 plus 6, so 66 inches. So if we said less than 66 inches, again, of course, you could go with the idea of using a z-score, right? And we could take that process, but it's kind of, to me, is I don't really understand why they would want to go through this because you got to use a calculator anyway. So even if you go through this process, you're still using a distribution function within a calculator or Desmos. So I don't really see the need for the extra step for the use of the z-score. So honestly, I would have just gone straight into either my calculator or Desmos to do this. So if you want to try it, I'll do this one more time here. So if we said less than 66 inches in the calculator, I go into distribution, normal CDF. And so consider if I said less than 66, that means I'm going to go from negative infinity, which, by the way, if you don't know how to put this in, all I did was type in basically -1 times 10 to the 99th power. It's like the smallest number this calculator can handle. Realistically, though, if you were to just put in 0, you're going to get pretty much the same answer. So our upper bound is now 66. I'm going to keep in my same mean and standard deviation. And there's our percent. Right? So the probability of less than 5'6" would be about 12.7%. Throw that one into Desmos real quick. So again, I wanted you guys to see that, again, if you get rid of this number, the default is negative infinity. So I don't even have to put that in. I'm just going to put in my upper boundary, and there it is. So there's my percent. Gives me the graph. Piece of cake. So this was more of a reminder to myself to make sure I went through all the other tools for you guys, but obviously we just covered that. So let me go down to here. A little extra practice. So the heights of adult men can be described by the normal model. Here's the mean, standard deviation, same numbers. The shortest 20% of American men are less than what height? So this is super important. In fact, let's give this the title. So if you ever look back on this, you remember where this came from. This is now going to be an inverse normal process. If you look at the last examples that we just did, we were finding a percent on every single case. That's what made it normal. Well, in this event, they're giving you the percent, and they're asking you what the x value was. Okay, and so that's what now makes this the inverse normal process. So we need to know, in terms of our curve, so when they talk about the shortest 20%, they're obviously talking about the bottom 20%. So in other words, they're talking about this area right here of the curve, which is 20% of the area. All right, so this is what they're describing to us. Our goal is to figure out what number represents the bottom 20%. So we're looking for now an x value to figure that out. Okay, so this is our inverse normal process. On the graphing calculator, go back into distribution. Option 3 says inverse normal. Choose that one. So they're going to ask you 3 things. They want the area under the curve. They want the mean, and they want the standard deviation. So keep in mind for this, guys, that when this calculator does this, when it just says area, it will automatically use the area to the left of x. Okay? So if they ever give me an area to the right, which is what we're going to deal with here in just a minute, I'm going to need to subtract that from 100% in order to put that into my calculator. Unless you have one of the newer versions of this calculator, it'll actually have the option here that says left, center, right. Then you can actually dictate what area the calculator is using. And so if you highlight the word left, then it would fit this description because we're talking about the area to the left of x. If they were to refer, instead of the bottom 20%, if they were to refer to this as the top 80%, which would be the same x value, but you could identify it either way, right? The bottom 20 is still identified by the same x value as the top 80, the same separation point. So if they would have said the top 80%, well, in this calculator, I still am going to put in 20% because I need the number to the left of x. But if you had the option that said left, center, right, you could highlight the word right and put in 80%, and then you'd get the same answer. So anyway, so area to the left of x is 20%, so 0.2. The mean, 69.2. Oops. Our standard deviation is 2.8. And there we go. So 66.8 would be that x value right there. So if we were to lay out all the numbers on this bell curve, right, the bottom 20% would be marked by 66.8 on the x-axis. Okay, so let me do it one more on this, and then I'll switch over to Desmos and show, we can take a look at how to do it on there. So what if they refer to the top 1% of people? So now they're talking about a number to the right. So top 1% would be way over here, right? So this area under the curve is representing the top 1% of people. Okay, so in this calculator, again, when I go into inverse normal, this calculator will always work with the area to the left of x. So for this one, I can't put in 1% because my calculator would think I'm talking about this guy, right? So if there is 1% to the right of x, that means there's 99% to the left. So now I could look at this and get the number of 75.7. So that represents that x that you see right there. Okay, so that's how we do it on graphing calculator. Let me switch over to Desmos. Okay, so here's how we put in the inverse normal. So again, you bring up the calculator, go to your functions. Under distribution, you want to go to inverse cumulative distribution function. Right, so here's a little bit weird about this one though, is they need to know now, what are you taking the inverse of? Well, we are taking the inverse of a normal distribution function that looks like this. And so now we're going to put in the mean and the standard deviation, just like we did before. So mean, comma, standard deviation, close your parentheses. And now there's one last piece, is it needs to know the percent left of x that you're finding. So remember the first question said the shortest 20%, right? So the bottom 20%. So now if I put in comma 0.2, it gives me that answer. Okay, and so 66.8, same answer we got on the calculator. So this one's just a little tougher to remember the steps for. So practice helps on this one, or you can always even just sort of take a screenshot or a picture of this, and this would be a good reminder of maybe how we did this. The easy thing is once you have all this typed in, it's easy to switch areas. So now if they wanted to refer to the top 1%, remember that's the same thing as the bottom 99. And so there's your 75.7. Same thing we got on the calculator. So this is the way we can put it in with an inverse. I thought we could see the graph for this. I haven't toyed with this enough, but I thought we would see the graph. I don't know. We'll figure that one out. Oh, you know what? If you were to just graph, to get rid of the inverse, if you were to just graph the normal distribution the way that we did on the previous example, then you would see the curve, and then you could put this in separately, and then you'd actually be looking at a point on that curve. So anyway, so that's how we do the inverse normal. Let me jump back to these guys. And this is our last page. The last page on this is just a solution page. So the reason I kept this in here is they go through the explanation if you would have done this with z-scores. And so again, I kind of wanted to keep that in here just to remind you there is that idea of z-scores, and those do play a role in other areas. Just we don't really need the use of z-scores for what we're doing right now. But I wanted you to at least know what they are, how they work, how you could still use them in the calculator. I just think the other ways that I showed you after that are a bit quicker and a bit easier to use. But at least we know what they are and what they stand for. So the bottom slide was kind of the same thing, explanation of how we got those same results but using z-scores. But that'll do it for this chapter.